Hello. In the last video, we talked about whether energy was absorbed or supplied by the element. In this video, I'd like to start putting some numbers to that. Knowing how much energy is absorbed or how much energy is supplied is very important when you're designing a circuit. For example, if too much energy is supplied too quickly, we might burn out our light bulb. We might damage our laptop. On the other hand, if not enough energy is being supplied, perhaps a light bulb won't turn on, or a laptop won't work properly, or a car won't start. So we need to know how much energy is being delivered to my elements at a given time. Before we talk directly about energy though, it's really instructive to talk about power. If you remember, power is the rate at which we use energy. So it's not just the energy, but it's a time dependence on that energy. The unit of power is joules per second, which we call the watt. What's interesting in circuits is that we can actually derive the watts from the other units we've already seen. If you recall, voltage is a joule per coulomb. Amperage, or current, is a coulomb per second. If we multiply those two together, we get a unit you may actually see is called a volt amp, and it's a joule per coulomb multiplied by coulomb per second. And if you remember unit conversions, my coulombs will go away, and this gives us joules per second, also known as watts. So it seems as though we might be able to say that in a circuit, the power is the current times the voltage. We're not going to quite stop there though. So power of t, typically everything is a function of t. So if I don't write in the function of t, you can just assume that it's already there, is equal to voltage of t, okay, times current of t, times something else, which I'm going to call the sine. If you remember, we talked about whether current delivers or supplies or absorbs energy, to an element. Similarly, whether the element absorbs or supplies energy. That's where this sign comes in. There are certain conventions that we use when we're talking about circuits. As long as we all agree on the convention, all of our answers will eventually agree in the end. Even if in the intermediate stages they don't quite agree because you've chosen your current to go one direction and I've chosen it to go in the other. That's where this sign comes in. So let's take a look at what that sign is in a particular circuit. So I once again begin by drawing my generic circuit element. And right now I'm going to put a negative here and a positive here. Remember, that means that A is the low energy terminal and B is the high energy terminal. There's a voltage VAB developed here. And now let us say that current I of t is entering this way, and I of t is greater than 0. What we're going to say is because current, that's BC means because, enters the low energy terminal, power is voltage at t times current of t times -1. This might give you a bit of an answer as to why we used a negative sign to represent the voltage at A. It allows us to keep track of the sign coming in for this power computation. So in this case, my voltage was VAB. My current I just gave you is I of t. So this might more compactly be written as negative VAB times I. Recall that this means that current gains energy, but last video we talked about not considering what happens to the current's energy, but considering what happens to the element's energy. If the current gains energy from the element must lose energy. And that's where that negative sign comes in. The element is losing energy at a rate of negative VAB times I. This is how quickly it's losing energy to the current. Similarly, if we have the other situation, A and B, negative and positive, and again I'm setting up so VAB is greater than 0, but current is entering this way, and again we have to say that I of t is greater than 0 just to keep the sign straight. Again, as we showed in the last video, if I of t was not greater than 0, we have to flip its direction and its sign. But for now we're assuming that the current is entering the high energy terminal. Then this is where my sign comes in, and power of t is V of t times I of t times positive 1. Now which voltage? If you recall, there was also a VBA this way. However, we're using a convention that allows us to ignore VBA. Why? Because of this sign variable. So if you remember, VBA is negative VAB, but we'd like to start working only with positive numbers. That's something I said in the last video. To do so, power of t in this particular case is going to be VAB times I times positive 1. Why? The current is entering the high energy terminal and leaving the low energy terminal, which means the current loses energy and the element absorbs energy. So what this means is the positive sign indicates absorbing energy. If it seems a little bit confusing to you, and you'd rather work with VBA, then just remember that if you do that, you have to keep your signs consistent. If VBA is a negative, then you also have to consider that the power is going to be negative. However, since you're going the opposite direction, the power is still absorbed by the element. It's easier to start with the voltage across the element being from the low energy terminal to the high energy terminal, and make sure it's always positive. Then adjust for the sign afterwards. Let's do an example. So the question that we're going to ask ourselves is, what is the energy, or the power, and is it supplied or absorbed? And I'm going to throw a bit of a curveball here, because what I'm going to say is this voltage here is negative 10 volts. And to even further complicate matters, this current, I of t, is going to be negative 8 amps. So remember, we want to know what is the power, and is it absorbed or supplied. So what do we do? Well, unfortunately we have these negative signs. You'll notice that I didn't do something. I didn't say whether this one is a low energy terminal or this one yet. Let's resolve that. If moving from A to B causes us to lose energy, that implies that A in this case is actually the high energy terminal and B is a low energy terminal. So I'm going to redraw just that part. I'm going to keep I of t the same direction and the same sign right now, and I'm going to flip the sign and flip the direction. I'll show you what I mean. I'm going to keep my terminals named A and B. So what's really important to notice is that my A is still there. I didn't flip the element. I'm just flipping the arrows. This now is VBA, and it is given as positive 10 volts. This is the negative, the low energy side, and this is the high energy side. And now I still have that current I of t is negative 8 amps. Let's now deal with that negative 8 amps. If you remember in the last video, I said it's very important to keep your signs straight. This is what I mean. We want to make sure that we can go back to those two cases we talked about before, which is the high energy circuit or terminal, which is the low, and which direction is my current flowing. So let's redraw everything one more time, doing everything in stages. We have A and B like before. B is the low energy terminal, A is the high energy terminal. We have positive 10 volts developing this way. And to handle the current, we have to flip the direction that it's going and also flip its sign. So it is going this way, and I of t is positive 8 amps. Now, if you can take a look, positive current is entering a positive terminal, which means the current is losing energy. It's going down in energy. The power is 10 volts times 8 amps times positive 1, which is 80 watts. And because the power is positive, it is absorbed by the element. So, to recap, what we did in this entire example, going right back up to the top, is we had to handle these negative signs. We had to ask ourselves the question, which terminal is the positive current entering? Does positive current flow into the higher energy terminal or the lower energy terminal? In order to answer that, I had to make sure that my signs and my directions were consistent. Notice something else that I did here, is the names of my elements don't really matter. Which one is A and which one is B, as long as it stays the same for the entire question, doesn't really make a difference. So, I just looked at, does positive current enter the positive terminal or the negative terminal? I kept my voltage and my current to be positive so that it would have an easier time computing the power. That's essentially all you have to do to make these judgments happen. Keep your signs consistent, keep the direction consistent, multiply everything together, and at the end, you and I will both agree that 80 watts was absorbed. Thank you.